So we are going to talk about the hypothesis testing, and now we will use an example. So you probably already have seen one example in the transcript of the lecture. It was the one about the grades in the school and about the quality of teaching going up or down. But I thought that it would be good to look into some maybe more real-world examples. So one place where hypothesis testing is used quite extensively is in medicine. So you may be testing a new treatment or a new drug, and you want to be sure that it really makes a difference. So let's say we have some disease which goes kind of hard and ends after about 30 days. So population mean is 30 days, with maybe a standard deviation of 3, just some numbers out of thin air. And now you are testing a new drug, and you tested it on 1,000 subjects, and you have a mean value of 25 with a standard deviation of 7. And as we already told last time, there is a thing called sampling error. So when you take a sample from the population, most of the time, statistics for that sample won't be exactly the same as population parameters. So for example, if a true population mean is somewhere here, so your sampling distribution looks like this, then your sample won't be right in the middle. It will be somewhere here, for example, or here, and so on. So the value of your sample mean will be different from the value of population mean. So let's say here we have a population mean, and here we have a sample mean. And now, in this example, so we used the drug on those people, and we want to know. So we see that the sample mean is less than the population mean, and we want to know if that change is, if that is a change due to the usage of the drug, or maybe it's just a sampling error. Maybe our sample just falls somewhere here. Maybe it's not the real change. So how do we know that? So last time we told about the confidence interval, right? So when you have the sample mean, you build a confidence interval. So you find the standard error and you say, okay, the true population mean should be between x plus sampling error and x minus sampling error. So you find your interval and you say, with some level of confidence, we chose 95%, but it might be a different number. So with some level of confidence, our true mean is inside that interval. Now, we will do something similar, but it will be the other way around. So I want you to remember the formula we started with. So we said that the true population mean no, it was the other way around, right? So the sample mean is a population mean and we are subtracting something to the mean from the mean value, and it will create the interval again, maybe something like this. And then we will just look if our sample mean is inside that interval, then probably it means that that the difference between sample mean and population mean is just a sampling error. But if it's outside that interval, then that should mean that it's not just a statistical error, it's a real difference. So maybe if we have something like this for our confidence interval, and our sample mean is outside that interval, we will say that, okay, it's not a sampling error. The mean really went down. So whatever we did to those subjects is making a difference. Okay, but how do we do it? So first thing, we should state our hypothesis. And there are two different types of hypothesis. One will be a null hypothesis. So it's called null hypothesis. And it's usually denoted by H0. So null hypothesis always states that there is no change, there is no difference, there is no connection, and so on. So in our case, our null hypothesis is that the drug had no effect and the real duration of the disease did not went down. So it's not less than 30. And we see that the sample mean is less than 30, but what do you call it? But the null hypothesis tells us, well, okay, your sample mean is less than 30, but it does not mean anything. It's just a sampling error. Okay, so null hypothesis is that our mean value is still 30. That there's no change. In fact, if we were true clinicians or pharmaceutical specialists, we will choose a different null hypothesis. So if I'm a doctor or if I'm a chemist making drugs, then what I'm interested in will be whether or not the disease time, the time it takes for a patient to heal up, went down. So if my drug is working, then that time should become less. And I'm absolutely not interested in whether it became more. So it became less or it did not. And in that case, my null hypothesis would be a mean value is more than or equal to 30. So I'd say that, oh, sorry. So my null hypothesis is a mean is still not less than 30. Or if we translate it in the context of our example, it just means that the drug did not help diseased patients in any way. Okay, so that's our null hypothesis. And the second type is alternate hypothesis or alternative hypothesis. Call it whatever you want. So alternative hypothesis. Again, we can mark it as HA or H1. Both markings are used, so whichever you like more. I will use HA. So our HA will be that there really is a difference. So it will just be the opposite of our null hypothesis. Mean is less than 30. So what it means is that this 25 we are seeing here is not some quirk of our sample. It's a real change, and the mean value went down as the result of our treatment. Okay, so that's our first step in testing the hypothesis. We stated our hypothesis. So I'll mark it somewhere here. It's step 1, stating the hypothesis. Okay. So we have stated our null hypothesis and alternate hypothesis. And we want to check whether null hypothesis is false or not. This is not a branch of maths where we can have 100% level of exactness. It's statistics, it's connected with random things. So whichever calculations we make, whatever results we get, they are always random in some way. And so, for example, when we were building a confidence interval, we chose the level of confidence. We said, I'm 95% sure that my mean value is between this and this, or maybe I am 80% sure, and so on. The same applies here. We need to choose a level to which we, okay, so how do I put it in words? So let's call it confidence again. So we need to choose a level of confidence. For example, when we were building a confidence interval, we chose a confidence of 95%. And there is a thing, there is the opposite of confidence in some sense. So if I'm 95% sure that I am correct, then it means that I allow for 5% chance of a mistake, a 5% chance of an error. And this thing has its own name. So 5% in this case, again, it can be any number, you choose it. It's called significance or level of significance. So the second step we need to do is choose a level of significance. And I will choose a 5% level of significance. So what does it mean is that if the result of our test tells me that my null hypothesis is incorrect, so if I will reject the null hypothesis, then there is a 5% chance in this case that I'm making an error by rejecting a null hypothesis. So in fact, this number, 5%, is a level of the risk we are going to allow. So testing the hypothesis is a risky thing, and the exact level of a risk you allow is this, and it's called level of significance. So that's our step 2. Step 2 is just choosing the level of significance. And let's take a deeper look at that thing we call significance. So we have our null hypothesis H0. It can be true or it can be false. So there is 2 possibilities. Either our null hypothesis is true or it is false. And now, as a result of our test, we can either reject the null hypothesis, so test tells me that it's not correct and I reject it, or we can not reject it. If our null hypothesis is true and we rejected it, we made an error, right? Because we rejected the true thing. It was correct, it was good, it was true, and we rejected it. And it's called type 1 error. We are making type 1 error when we are rejecting a true hypothesis. So for example, your friend came to you and told you something which was true, and you called him a liar. That's the type 1 error. If our null hypothesis is true and we did not reject it, then we did everything right. It's okay. There is no errors. If it's false and we rejected it, again, we did everything right. And if the null hypothesis is true, but we did not reject it, we made a type 1 or type 2 error. So in some sense, type 1 error is when you do not believe someone who speaks truth. And type 2 is when you believe a liar. And there's a probability for both of those error types. A probability for type 1 error, probability of a type 1 error, of making type 1 error, is our alpha, our significance. So significance, our significance, or the level of risk as we call it, is just a probability of doing a type 1 error, a probability of not believing the truth. Then there's same thing, so the probability for making type 2 error, and it's called beta. No, it's marked beta. As far as I know, it does not have a separate name for it, and people usually just call it beta level. So you have your alpha, which is a level of significance, and it's the probability of you believing, not believing the truth. And there is beta, which is the probability of you believing a lie. Both of those things are errors. Okay, so our step 2 is choosing that level of significance. And we will choose 5% for the sake of example. In fact, it's totally up to you. And if you want to be more sure, you can choose lower level of significance, 2%, 1%, and so on. Or you can choose higher level of significance, like 10%. So the smaller, the less, less your significance, the more sure you can be in your results. Okay, so next thing, we are working with some numbers, and to check those numbers, we will need more numbers. We can't just argue in words or philosophize about that. We need exact measures to be sure about our decisions. And those measures, those new numbers we will use for testing the hypothesis, are called test statistics. There are different kinds of test statistics, and we will use our old friend Z statistics in this case, or Z score, or Z distribution, right? So that's the statistics we will use in this example, because we know something about the population. We know where it is. Yeah, we know the population standard deviation, and that calls for using the Z value. So we are choosing for a mean value of population, and our Z is connected with both our sample mean and the true population mean and standard deviation. We have all those things, and it just invites us to use the Z statistics in this case. If you are checking for the mean value, but you don't know the population standard deviation, then you will use a T statistics. Both of them were used in building confidence intervals, Z and T. However, there we used the table to define Z or T based on the level of confidence we want to use. In this case, we will do something similar, but not the same. Okay, so this thing is T statistics. And that's our step 3, choosing a test statistic. Okay, so what's next? Next, we need some kind of a rule which will tell us how do we get our outcomes, so to speak. So that's our step 4, to formulate the decision rule, to state the decision rule. So now we will look at it.
But what was the third step?
Oh, choosing the statistics that we will use. So
You mean Z or T statistics? Yeah?
yeah, in this case, it's Z or T. In fact, you have different kinds of statistics. So there is a thing called chi-square, so chi-square statistics or R statistics and so on. They are used in different places for different cases. But if you are checking for the population mean, if you are testing for population mean, then you will choose between Z and T. Later, when we learn about the correlations, we will look at another type of test statistics. So we will use R statistics. But for now, yeah, it's choosing between Z and T. And we know the population standard deviation, that's why we choose Z in this case. If we did not know it, we will choose T.
One more question. What was beta? For example, alpha was probability of making type 1. And
Yeah,
beta
beta is probability of making type 2.
Type 2. What about these two slashes you wrote?
I just did not want to rewrite this whole phrase. So beta is probability of making type. Okay, so I see now that there is a thing I need to fix something. Okay, now it's correct. So probability of making type 2 error is beta, and probability of making type 1 error is alpha. It's these two cells in our table. Okay, so we have our test statistics. We have chosen it. We decided that we will use Z statistics. In fact, we can go ahead and calculate it. So in our case, Z statistics is, our sample mean is 25. Our population mean is 30. So our null hypothesis is 30. And the population standard deviation is 3. And sample size is 1,000. So we can calculate this thing. It will be kind of easy. And let me do it, in fact. Times 5/3. Oh, whoa. So our Z statistics, or our Z score, is approximately 52.7 in this case. For this case. It's strange. Did I do anything wrong? No, probably not. So we have our test statistics, we chose Z, and it's 52.7 in this case. Oh, minus 52.7. Let me fix that. Okay, now we need to know how do we use it to decide if we reject or not reject the null hypothesis. So now we came back, we see that we chose a level of significance of 5, and it means that we need a level of confidence 95. Now, let me again redraw the graph. Here is our previous old mean value. I can build the 95% confidence interval. So that will be my mean plus or minus 1.96 standard deviation over square root of n. And in fact, let me calculate it. So 1.96 times 3 over a square root of 1,000. So right now I'm doing the same thing I did damn. Oh, no, wait. So we don't need this part right now. What is this 1.96? It's a value of Z for 95% confidence interval, or the value of Z for 5% significance. So let me write it like this. What's wrong? Okay, so now it should be all right. Z for 0.05 equals 1.96. So let's imagine that boundaries of this confidence interval are somewhere here, maybe, and here, just for example. So what happens if my sample mean is inside the interval? It means that the mean value did not change. So it means that our null hypothesis is correct. So inside this interval, my mean value is still equal to its old value. So 30 in this case. Yeah, okay, so for some reason it's acting strange. Now, if we move to this part, if our sample mean is somewhere here inside this area, that means that my mean value is more than 30. And it's still in compliance with my null hypothesis. Because in the null hypothesis, we stated that mean is more than or equal to 30, right? Yeah, here it is. So the blue area on my graph is for mean equal 30, and the green area is for mean is more than 30. And both of those are when null hypothesis is correct. And now, if my sample mean is somewhere here in the left tail, then it means that mean became less than 30. So in this case, we will reject the null hypothesis. We won't keep it. So now we have our rule. For our null hypothesis to be rejected, my value of z should be less than minus 1.96, because let me just rewrite this. We have a lower boundary, which is old mean value minus 1.96 times whatever is there, sigma over square root of n. So minus 1.96. And our upper value is mean plus 1.96, again, sigma over square root of n. So we see that minus 1.96 is in some sense a boundary between rejecting and not rejecting the null hypothesis. And our rule is reject the hypothesis if z is less than boundary, and not reject it if it's more than boundary. We formulated our decision rule. Our next step would be making a decision. So we know the boundary, it's minus 1.96. And we know our value of z. So my z is minus 50, was it 57.2 or 52.7? 52.7. 52.7. And my critical value or boundary value, I'll call it a critical value, is minus 1.96. And I see that my z is less than z critical. So what that means is that we reject our null hypothesis. So after using the drug, our patients are really recovering faster, so to speak. The disease is lasting shorter times with the drug. Okay, so that's our step 5, making a decision. And then we have step 6, which is interpret the result. So you have your numbers, and you made your decision. You say, okay, with 5% level of significance, I can say that we reject the null hypothesis. And then your next step is turning that. So what I told now is some kind of a mathematical spell. Now we need to translate it into human language and apply it to whatever real world problem we were doing. And that step is this interpretation step. So after you did all the calculations and whatever, you need to interpret your results. You need to make them a real world sense. And that will be the end of your testing. Now, I want you to look at one particular thing. So here, we said that we are rejecting, maybe I will use this. So we are rejecting our hypothesis when Z is in this range, in the left tail of a distribution. And it's not there. If it's here, then we do not reject it. So our rejection range is in one tail of the distribution. And that's why this test we did now is a one-tail test. And in fact, when you are doing one-tail test, your Z value should be slightly different. So we used 1.96 because we know from the confidence interval thing that Z for 95% confidence is 1.96. But when you are building a confidence interval, you have two boundaries, upper and lower. So in some sense, you have two rejection zones. Now, here in our example, it's not like that. We have only one boundary, only one rejection zone. And in that sense, in that case, our critical value should be similar. So to define it, we will look at the Z table. Here it is. And the entries in the table are, what do you call it? They are showing exactly this area. They are showing the area here, our rejection area. And we know that it should be that this part, oh, okay, let me clear it. So we need 5% to be here in this area. So I go to the table and I look for 5% entry. Here we have, oh, no, it's still too small. Let me look further. We need 0.5. And it's somewhere here. I see 44, 43, I see 54. I'm not, okay, so here. These two entries. Yeah, that's 5.05% and 4.95%. 5% is exactly in the middle between those two. So I see that it's so it's minus 1.6. And now I need to check these two columns. So that's 1, 2, 3, 4, columns 5 and 6. And I will take whatever is in the middle. So 1, 2, 3, 4, 5, 6. Oh, sorry. I need to move it a bit. And I better clean it up. So that's these two columns. Right in the middle between them is 0.045, and we know that for this part we had minus 1.6. So it means that our critical value will be minus 1.645 instead of 1.96. It will be 1.645. Okay, that's because our test is one-tailed. If it was two-tailed test, like this, then your critical value will be different. You will need to take, so what you will need is, if you want two tails to contain 5% significance, then one tail will contain 2.5% significance. And if I look for 2.5% here in the table, it's here. So let me mark. So 2.5 is here, and I see that Z is minus 1.9, and it's the column 1, 2, 3, 4, 5, 6, 7. So if I go up and look, it's 0.6. So minus 1, 9, and then we have this. So minus 1.96 for two-tailed. So we used, in our test, we used the value for two-tailed test, which is 1.96. But in fact, the true value we should have used is minus 1.645. Well, here in this case, it changes this, but it does not change anything because our Z is still way much smaller than our critical value, right? But sometimes you might have something like your Z is 1.8, and when you use one-tailed test, it's a rejection. And when you use two-tailed test, it's not a rejection. So always be mindful of what kind of a test you are doing. So let's make a break now. And then after the break, we will do one more example, which will be two-tailed, and maybe it will be with T statistics instead of Z statistics.
I did not understand. Where did you get 1.6?
So let me go back to the table. I want 5%, right?
Uh-huh.
I want 5%. So let me clean up. And I see that 5% is, so let me mark that place. So if you look here, okay, so here, now need it to be brighter. So here we have 5.05 and 4.95. Is it on the screen? Can you see the table?
Yes, yes.
Yes, yes, yes.
Okay, nice. So we have 5.05 and 4.95. And we need exactly 5. I say that 5 is in the middle between those two. So here. Now, to find the first digits, I just look at the start of the row in which they are. And there's a minus 1.6. So
Okay.
it's minus 1.6. And then after that, so it's 1.6, I need next digits. To find those next digits, I will go to the top of the table and I will look at the appropriate columns. So it's this column and this column. And I need to find what's in the middle. Well, in the middle between 4 and 5, we have 4.5. So next two digits would be 4 and 5. That's the usage of the Z table. So in your books, you have another kind of Z table. Again, let me clear it. Here you can see that the values in the table are for this part, for the tail. And if you take a book by Mr. Lind and go to the appendix, there is also a Z table, but the numbers are different if you look at them. And that's because Mr. Lind gives values not for the tail, but for this central part. And on the internet, you have both kinds of Z tables, the one for tails or the one for centers. And usually they have this kind of pictures which show you what kind of Z table it is. You can use both of them. So for example, if instead of a tail table, you have a center table, and you still need the 5% tail, so which means you need this part to be 5%, then it means that this is also 5%. What? Okay, so this is also 5%, and whatever is in the middle is 90%, and that means that this half is 45%, for example. So instead of looking for 5 in the tail table, you can look for 45 in a center table, and you will get the same value for Z.
So it means that in the last step 6, when we are just like interpreting the results, we should just like find that percent which was on risk, yes? In risk. 5%, that is kind of 0.05, and we should just like find it in the table, yes?
Yes, so that's for your step 3 and 4 when you formulate your decision rule. After you chose it's not for step 6, it's for this step where you find the boundary. So we need to fix that here too, right? It should be minus, yeah, so it should be minus 1.645 instead of minus 1.96. The table is needed on this step to find your boundary, to find your critical value. Interpretation will not require you a usage of any tables or calculations. So the step 6, where you interpret your results, is just when you translate everything from the language of the mathematics into the language of whatever problem you are studying. So here it's maybe a treatment of diseased patients. I have an example in a text transcript which I uploaded to Canvas announcements. There it's about the grades of the students in the school and so on. And in fact, this method itself can be applied almost everywhere, and it is applied almost everywhere. So the real underlying problem might be everything. It might be economics, it might be science, or it may be something connected to teaching, to medicine, to anything. And the statistical toolkit is just the same for all those cases.
So in this case, in this problem, how do we make the interpretation?
Well, we see that we need to reject our null hypothesis. And it means, so here is our null hypothesis. If I look at the condition itself, it tells me that, in fact, it just tells me mean is not less than 30. And the first objection would be, but I have mean less than 30. And they say you, well, yes, you have the mean value, which is less than 30, but it's just a sampling error. So when you take samples, you make errors. That's why you get the mean value of less than 30. It doesn't mean anything. But now we made a hypothesis testing, and the test told me that I should reject this. That means that I accept this. And it tells me that mean is less than 30. So it really is less than 30. It became less than 30 and so on. So for this example, my result that null hypothesis should be rejected just means that, give me a moment. It's okay, it's working. So it means that this 25 is not just some kind of an error. It means that there is really going something that made our mean value smaller than it was. So if that's the results of a drug testing, and the mean is a mean value, let me formulate that. So if that mean value is a mean duration of a disease in a patient, then test is telling me that my drugs and treatment that I used on that patient really did shorten the duration of disease. So it did really went down. It's not just some kind of a random quirk. So I guess for a second part, we will choose something maybe a bit more intuitive, maybe just the example from the transcript.
So
and hopefully it will be more clear.
So our interpretation is that we need to reject no. Yes?
No, it's our result. Rejecting the null hypothesis is our result, but the null hypothesis itself is just some mathematical statement. Its mean value is more than 30. That's our null hypothesis. And we need to connect it to some, to the real things that give rise to this test. So let's do this. Let's take a break now.
Okay.
Then we will take another example, and we will take an easier example where the connection between a real world situation and this hypothesis test thingy will be more clear.
Okay.
Okay, so just a moment. Yeah, it's here. I'm pausing the recording for now. Let's go for another example. And this time we will use t-table. So let's say, well, not let's say, I really do have students. And let's say before the quarantine started, mean grade, average grade for my students was 90 points. And sadly, I was not aware that I will need that information, so I did not calculate the standard deviation. I only know that the average grade was 90 points. Now, it's already 3 months, or is it more? I guess it's more, right? It's more like 4 or 5 months of quarantine, and the studies are online and so on. And I decided to check the average again, and I choose 50 students. I test them, I assess their works, I calculate the average, and I see that the average is 87 points with a standard deviation of 10, sorry. So, oh, in fact, let's make it 9. Let's make our own life a bit easier. Okay, so it's 87 points with a standard deviation of 9. And again, I'm starting to worry. I'm thinking, well, maybe this online study thing is not very good. Maybe it led to the points dropping, because a new average, sample average, is less than the previous population average. Then I remember that I'm teaching statistics, and that there is such thing as a sampling error. So maybe that difference is just a sampling error. Maybe I just choose the sample from the lower end of the distribution, and that's why I got lower average. And now I want to know for sure, did the average grade change, or is it just a sampling error? So I can go as in the previous example and choose my null hypothesis to be mean is equal to or more than 90. But then again, I start thinking, I think too much, that, well, there is a possibility that online studies made it better and the real average went higher than it was. So let me check not for the drop, not for the decrease, but for any change. So my null hypothesis will be that there is absolutely no change. The grades did not become higher or lower, they stayed the same on average. And then the null hypothesis will be that a mean value is 90, which is the same as before the quarantine, as we see here. That means that my alternate hypothesis will be that there is a change, that my mean is not 90. It's either more than 90 or less than 90. So I stated my hypothesis. So that was step 1. Now I need to choose the level of significance. So I want to be very sure. So I choose lower significance. I choose 1%. So I want to be 99% sure that my testing is correct. So next thing, step 3 would be choosing the test statistics. I see that I don't know the population standard deviation, but I know the sample standard deviation. And that means that I will use t-statistics.
Where did you get 0.01?
That's the significance. You choose it yourself. So in previous example, we choose 5%. Now I'm choosing 1%.
Okay.
So it's just how sure you want to be. I want to be 99% sure. So I have to allow for only 1% risk of an error. And that's it, 1%, 0.01. Okay, so now I will have to use t-statistics, and it's my sample mean minus previous true mean divided by S over square root of n. Oh, okay, there was no need to change the standard deviation. Okay, whatever. So 87 minus 90 over 9 and times square root of 50 because our sample size was 50. And now let me calculate that. So square root of 50 times 3 over 9. It's minus 2.357. That's our t-score. Now the rule, it was our step 3. Now we are looking for any change, not only for decrease, but also for increase. So I have my previous mean, I have the confidence interval for it with that 1 point significance, 1% significance. And now I will reject if my sample is here, but also I will reject if the sample is here, because my null hypothesis is that there is absolutely no change, no growth, no drop. So if there is a decrease, I reject. If there is an increase, I again reject. So this time our test is two-tailed test because I reject on both left and right tails. That means that if my z-score, oh, it's not z-score now, it's t-score. If my t-score is less than minus t-critical, or if it's more than t-critical, I will reject. That's my decision rule. And that's the step 4. Okay, so now we need to find the critical value. For that, I will need a t-table. Again, you can find it online, or you can take it, you can look it up in the appendix of your textbook. So here, if you look, we have, here we have significance levels, and we have them both for one-tail tests and two-tail tests. We chose a significance level of 1%. So it's here, this column. But now we have some additional things. So here, if you look, there is a thing that's marked as DF, and that DF is degrees of freedom. And degrees of freedom is just n minus 1 in this case. You might remember that from the time we learned about standard deviation. We have n numbers, but those n numbers are not all totally random, because their the mean of their deviations should be 0. And that imposes a restriction on them, and one of them becomes not free to choose. So that's why n minus 1. In our case, we have a sample size of 50. So our degrees of freedom will be 49. And let me mark it one more time. We are looking for 1% two-tailed test. So it's this column. And I need to find the 49 degrees of freedom. Okay, let us stop here. Let me bring this again, this column. This column. And I don't have 49 here. I have 40 and 60. And that's these two rows. 49 is approximately in between those two. almost in the middle. So if I take the average of those two, so 2.704, 2.704 and 2.660, that should give me a t-score for 49 degrees of freedom for a sample size of 50. So those two values are here for 40 and 60. So 2704 and 266. Now I can just go back. 2704. What's wrong with it? Okay. Looks like there's...
It's 5.364. And if we divide to 2, average will be 2.682.
Over 2. So 1364, 65684. So it's 2.684, right? Ah, 682. Okay, good. 682. So that's our critical value. And if my t-score is between minus 2.682, what the hell is going on with my screen? Yeah, so if my t-score is between minus 2.682 and plus 2.682, I accept. I won't reject. And if it's outside those boundaries, then I'll reject my null hypothesis. So reject here and reject here. Okay, so let's look up. Our t-score is minus 2.357. So minus 2.357. It's inside, it's not in the rejection range. And that means that we do not reject our null hypothesis. So we made a decision. That's our step 5. We don't reject the null hypothesis. Now we can go back, and our null hypothesis is that mean value did not change, that it's still 90. So if I want to interpret our result, not rejecting the null hypothesis, then it would mean that my mean value is still 90, and that the quarantine did not affect the quality of teaching in any meaningful way. So that 87 that I got is not because the grades really dropped, but because it's the sampling error. So some students have better grades. Let's say this is 70 points and this is 100 points. And excuse me. So there are, thank you. So there are some of them, there are quite many of them, which have points between, say, 85 and 90, for example. There are some of them with a very high points and some of them with a very low points. And most probably, I took my sample from this part, and that's why the average is lower than the population average. So it's just a sampling error. And it's not because I wanted it to be such way. It's because the statistics, the exact calculations told us that it's a sampling error. However, still, there is a possibility that we are making a mistake that there is a real change. And we can say that the chance of that is only 1%. If you choose different levels of significance, your results may differ. They may be, so for example, a hypothesis that is rejected at some levels of significance may not be rejected at other levels of significance. Usually when you raise your confidence level, when you make your, what do you call it, significance lower, then your acceptance rates grow. And that's because with larger so when you take higher confidence levels or smaller significance levels, your interval grows. For example, for 1%, you have something like this. Just as an example. So whole this area is the acceptance area for 1%. But if you change your significance and you choose, for example, like 5%, so it's only 95% confidence, then your interval becomes smaller and your acceptance range also becomes smaller. It's only this. And whatever is outside of this one but inside this one, so for example something that's here, it will be rejected for this level of significance, but it will not be rejected for this level of significance. When you move your significance level down, you broaden your boundaries. You make the rejection area smaller and you accept more hypotheses. So just to illustrate that, let's do the same thing, the test for the same data, but with a significance of 5%. Maybe our decision will change, maybe it won't, we will see. So I need 5%, 2 tails. So it's here. 2 tails, 5% is in this column. And now I go here, I find 40 and 60 again. It's these two. So 2.021 and exactly 2. Average of those two, average of these two will be 2. So let me put it somewhere here. Maybe here 2.0105. So that will be our critical value for 5% significance. Now let's go back. So T critical is 2.0105 and my T score is, it's here, minus 2.357. So minus 2.357 is less than minus 2.0105. So the same hypothesis will be rejected at 5% significance level. your decisions rely not only on the data, but also on your significance level. So usually when you speak, when you hear scientific reports or something like that, they'll always report their significance level. They will say something like, we have proven that this thing is true on a significance level of X%, and so on. Without stating the significance level, your results will not be readable, because we can study the same thing, we can test the same hypothesis, and I will reject it, you will accept it, or the other way around. And then we go to report and you say, well, I did a hypothesis testing and the hypothesis is true. And then I say, well, I did a hypothesis testing and it's not true. And it will be it's contradictory and it's misleading. So two people speaking about the same thing, but telling the opposite things. One of them might be lying. However, if you also report your significance level, so you say, I tested it on 1% significance and I do not reject it. And then I say, I tested it on 5% significance level and I reject it. Then we are still kind of contradicting each other, but we have different levels of significance and we are both telling the truth, and there's absolutely no incentive to call someone a liar or something like that. Well, but okay, the main thing is that, so your level of significance is important. And whether you are doing one-tailed test or two-tailed test is also important. As we have seen earlier, Z-test will have higher critical values for two-tailed tests. So for example, for 95% significance, you have 1.96, and for for one-tailed test, you have 1.645. So what's rejected in one-tailed test can be accepted in two-tailed test if your Z is between those two. So it also matters. And choosing the correct number of tails is also important. Okay, and there's a couple of things I want to tell you. So let's go back to our first Z-test. I'll clear this page and we will use it.
Could you please show how we get minus 2.357?
This one?
Yeah. Yes.
Yeah, I just used the formula. Sample mean minus population mean divided by sample standard deviation over square root of sample size.
Oh, got it. Thanks. That's all.
Okay, so if we go to our first test, or maybe we will use our second one. Doesn't matter. So let's just use whatever we have. Yeah, I will just slightly change my second test. I will add the population standard deviation and let it be 5, for example. Then we can use the Z-test, and our Z value would be 87 minus 90, which is minus 30, square root of 50 over 5. So why is it minus 30? It's minus 3, sorry. So let me calculate it. Times square root of 50. So my Z value would be minus 4.24 And if I do a 95% two-tail test, then my critical value would be 196. Minus 424 is less than minus 196. And we are rejecting the null hypothesis. We are saying that there is a real change in the grades of the students, right? And now we can calculate the additional thing. So let's remember this value of Z. It's minus 424.
Where did you get 3 minus 3?
87 minus 90.
It's okay.
So x minus mu. So I take that minus 424 and I go back to our Z table. So minus 424. Oh, okay. We don't have minus 424 here. Yeah, it's not good, but okay. So if your table has minus 424, whatever value of Z you are using, then you just use the table. And if not, we can use Excel. So Excel can calculate the needed probability for us. So let me just create a new table. So our Z distribution is just a normal distribution. Just a normal distribution with, so I want to calculate it for minus 494 or 424. And Z is a normal distribution with a mean value of 0 and standard deviation of 1. We want to take the whole area in the, the whole area to the left of my Z value. And for that, I will use this cumulative. So if you have negative Z, you use this formula, normal distribution with your Z value, 0, 1, 1. If you have positive, it will change a bit. We will come to that. So we can just calculate it. And it did not. Why? So what's the matter? Oh, okay. Okay. So I always forget that Russian localizations use. Okay, yeah. So here we have our number. It's 0.4 zeros and then 1. And that's called p-value. So you can find the p-value from Z table, or you can use Excel or any other calculator that knows how to calculate the normal distribution. So 0.00001. Is it correct? 4 zeros and 1. Yes. So it's called the p-value. And you might remember we said that our significance, alpha, is the probability of making a type 1 mistake. Well, in fact, when you are using the Z-score, the true probability of making a type 1 mistake is your p-value. And we see that here, in this case, it's very small, 0.00001. So let me check it one more time. Was it really 4 zeros? Yes. If I move to the percentage, it's 0.001%. So we allowed for 5% risk of making a type 1 error, but we only get 0.001. So it's much less than our allowance, than our significance. And that means that the results of this test are very credible. You can be almost sure that it's correct, that you are not making a mistake. There are, of course, another cases. So when your P is smaller than alpha but close to it, or larger than alpha and close to it, or much larger than alpha. So this case, these two cases are both strong evidence. So first is strong evidence that your null hypothesis is false. And this one, where your p-value is much more than alpha, is a strong evidence of null hypothesis being true. So it's a strong evidence. Then we have these two cases where P is either less than alpha or more than alpha, but close to it. So first one is an evidence that null hypothesis is false. And the second one is an evidence that null hypothesis is true. But in these cases, it's a weak evidence. It's not a very strong evidence. Yeah, okay, you can decide that H0 is false, but you can't be very sure about it. The chance of you making a mistake is very high. We can put it in different words. So if our p-value is much more or much less than our significance level, then it means that our z is much less than minus z critical, or it's much more than z critical. It's the case when p is much less than alpha. When p is much more than alpha, that means that your z-score is almost zero. So both cases are strong evidence of null hypothesis being false, or strong evidence of null hypothesis being true. The same applies to the t-score. So if your t-score is very far from your critical value, or almost zero, then again you have a very strong evidence of your null hypothesis being false or true. And there's one more thing you need to know. So we see that on the 5% significance level, the change in the grades is real, right? So this 87 is not a result of sampling error. But you might say, hey, look, even if the difference is real, it's only 3 points. Is it a great deal? Do we need to worry about that or not? So to answer that question, we have something that's called the effect size. So both in calculating the t-score and z-score, you used this thing. You take the difference, and you divide by standard deviation. So either by the population one or by the sample one. And then you multiply by the square root of a sample size. Now, if we do not include the sample size, then instead of our Z and T scores, we will have the effect size. So in first case, where you use the population standard deviation, it's called D criteria. So it's a D criterion, or D score if you want, and it has a name. So Cohen's D criterion. If instead you use sample standard deviation, then the same thing is called effect size. Okay. Oh, and one more thing. You have to take absolute values. So now we can calculate D score or effect size for our example. Well, this difference here will be 3, because 87 minus 90, and then the absolute value. Standard deviation for population was 5, if I'm not mistaken. Let me check, in fact. Maybe I am making a mistake. So let me just check. Yeah, it's 5 for a population, and it's 9 for a sample. So you don't need to calculate both of them. Usually you calculate the D score, and if you don't know the population standard deviation, then you calculate the effect size. Now, to illustrate, I will calculate both. So D score will be 3 over 5. And the effect size will be 3 over 9. So it's 0.6 and 0.3 approximately. And now there is a rule. So if your effect size is between 0 and 2.2, then it's a small effect. If it's between 0.2 and 0.5, then it's medium effect. And if it's more than 0.5, just more than 0.5, then it's large effect. Okay, so even if you have a significant statistical difference, but the effect size is small, then it's almost as good as there being no change, because the effect size is too small to be worried about. Well, in our case, if we use the Z-score, we know that the Z-score predicts that there is a difference. It tells us that the difference is real, and the D-score tells us that the effect is large. So those 3 points of difference in the average score, in the average grade, they are a big deal. It's a really significant drop. Even though just looking at it from the side, it's only 3 points, and it's almost as if there is nothing to worry about. And then the statistics tells you, hey friend, that difference is large as hell. You need to be panicking right now. And in fact, that's correct, because 3 points change in the average score of, say, 100 students means that either all of them have their grades lowered by 3 points, so all of them suffered some kind of a drawback in their teaching, or that some of them have a decrease of 10 or 20 or 30 points. So in both cases, it's a large effect. It's either a very large change in several persons, in several entries, or it's a small change, but in all of them. The most striking example of that will be the clinical tests of the drugs. So sometimes the new drugs appear and they perform the clinical tests of that, and they say you, hey, here we have shown that there is a statistical difference in well-being of a patients who use this drug and who do not use. And it's a real statistical difference, because hypothesis testing tells you that the difference is real, that it's significant. And then you know that, for example, without that drug, without using that drug, you will have a headache maybe. So let's say you have some kind of a strange disease that makes your head ache. So you have a headache 30 days in a month. And with that drug, you have a headache 29 days in a month. And it's not a real difference. That difference may be statistically significant, but it's not a real difference in applications. And that's when the effect size comes into play. So most of the time when your significant statistical differences are not good enough, are not real differences, your effect size will be small. And sometimes even the effect size can mislead you. That's why the step 6 is so important. So you need to interpret the results. So if you just take the report about the drug test, and the report tells you that there is a significant statistical difference, and the level of significance is 5%, and we have tested 10,000 subjects and so on, and you are some kind of a higher range official who decides whether the drug will be sold in the drugstores or not, you might be misled by that report and allow it. And then one day, you have that illness, you go and buy that drug, and you find out that the statistical difference they were talking about is only 1 day in a month. Instead of having a headache 30 days, you have it only 29 days. And well, believe me or not, it won't change anything for the better for you. So after you did all the calculations, all the maths, and you got your results, so the statistics did everything it can. After that, you need to interpret it, you need to look what it means in the real life. Is that significant difference a real difference that will reflect in practice? And that's where the statistics ends and your real life experience comes into play. Okay. Well, that's it. And if you have any questions or commentaries or something like that, I'm open for discussion.
I've got a question.
Yep.
Why actually we just like touched these kind of topics like the strong evidence, weak evidence, and the D criteria, effect size.
Oh, because you will need them.
I mean that, for example, if they will be given a task, they might just like ask specifically one of these formulas. Am I right?
Yeah, it might be that way. Or they may give you a data and they may ask, so for example, test the hypothesis. Will you accept it or reject it? Is your evidence strong enough to be sure that you did not make a mistake and something like that? So just as example, again, if we go to the drug testing, if you reject a hypothesis and your P is very close to alpha, so formally you are rejecting it, but your evidence is very weak. Most of the time in such cases, your drug won't be allowed for clinical practice because even if it shows the big difference, it shows it with a very small level of significance, with not significance, with a very weak evidence, and it leaves place for too high, for risks that are too high, and so on. And the same in economics. So some policies can really make a huge differences in theory, and then you make an experiment. Maybe you choose one city where you apply new policies, new economical policies, you gather the data, you perform the testing, you see that there is a statistically significant difference, but your p-value is not very small. So the evidence of that being a true difference is too weak, and that does not tell you anything about your policies.
Okay.
So you want to assess not only if you may believe that something is true or not, but also how strong can your belief be. And that's where you need your p-value. And then again, just like with drugs, you have a difference. So science tells you that it's a real difference, but for you as a real life people, that difference is nothing. So maybe a new policy that will make you earn, let's say, not $1,000 a month, but $1,000 and 2 cents. So that increase of 2 cents, it might be statistically significant, but it's nothing for you because, well, it's not a true difference, it's not a true change. And that's where effect size comes into play.
Okay. And here's the question: if P is much closer to the alpha, but we have the weak evidence, how
Yes.
to make it kind of a strong?
Well, one way would be to gather more data, to take larger sample sizes, and test your hypothesis one more time. If something, well, if on that level you will have the higher evidence, then good. If not, then maybe there is no way to make it higher. So it depends on the on what you are studying. But most of the time, taking larger samples helps, or you can change your significance level. So if you don't have a good evidence on, say, 1% significance level, then maybe 5% will be better for you, and so on.
Okay, got it.
Okay, anything else?
No. I think that during maybe when I will be reading, I can have some questions also.
Okay, you
I
can
will
contact
just
me.
like write.
Yep.
Thank you for the
Sure.
lesson. Sir.
Thank you. Anytime.
Thank you. See you
Bye bye,
soon.
teacher. Have a good day.